In this lecture, we will discuss on the concept of eigenvalues and eigenvector. And for this discussion, we will uh, focus on square matrices, basically of the where the matrices of the size n cross n and they are real matrices. Okay. Uh, let's say that A is some matrix of the size uh, n cross n as I have stated, and it is multiplied, or this matrix A acts on a vector which is of the size n cross 1. Okay, so A is of the size n cross n, B is of the size n cross 1. It will give you some vector. Let us call that vector as y, which is n cross 1 vector. Okay, now in some cases, what happens is for certain vectors, when this matrix A acts on them, for certain vectors, when A acts on this vector V, you get a vector which is just a scaled version of this vector. Okay, so this lambda here is the scaling factor. Okay, so the new vector that we get is basically a scaled version of the original vector. Now this scaling factor may be real or may be complex, and this vector that we are talking of, the V, it may be real or complex. Okay, the scaling factor here is called the eigenvalue, and the vector that you have used, V, is called as the eigenvector. Okay, so if you take, let's say, another vector W, which is some scaling of this vector V, and where A acts on W. Okay, so if V is a eigenvector and alpha is some scalar, if A acts on W, then you will again get lambda W, indicating that W is also eigenvector. Okay, so what you see here is a eigenvector associated with this eigenvalue is not a unique vector. There are infinite possible vectors that you can actually get. Okay, so what is this essentially saying is, let's consider a matrix 2 0 0 3. Okay, so in this case, if I consider the vector 1 0 and 0 1. So this is your y-axis, this is your x-axis that you would like to call them as, and this is the origin that you get. So here, if let's say this is the 0 1 vector, and let's say this is the 1 0 vector. So when A acts on this V, so V is 1 0. When A acts on V, you can verify that you get twice that of the vector V. So here, if you see, what happens actually is this vector V is scaled up by a factor of 2. So you get a new vector, which is a scaled version, that is 2 0. Similarly, if you take another vector, let's say 0 1, and if A acts on this vector 0 1, the resulting vector would essentially be 3 times this vector. It will be 0 3 when A acts on. So what you observe is the new vector is always along the vector over which along the eigenvector over which A has acted on. The new vector is just a scaling factor. Okay. So now if A further acts on this vector 2 0, you will get another vector which is 4 0, 2 times of that. Okay, and so on. Similarly, let's take another example. Let's have A which is 2 0, or rather 2 0 0 0.5. Let's say this is what it is. Okay, so here again we'll set up the axis. The y-axis and the x-axis. This as the origin. So if you take the vector 1 0, when A acts on this vector, you get a vector which is twice its length, which is 2 0. Okay, so this is nothing but A acting on 1 0. Similarly, if you have a vector, let's say of the size 0 2, when A acts on it, you get a vector which is 0.5 times the scale vector 0 2, which in this case is 0 1. So this 0 1 is nothing but A acting on 0 2. Okay, so in this case 1 0 and 0 2 serve as the eigenvectors for A, but 1 0 corresponds to the eigenvalue 2, because 2 is the scaling factor, so 2 is the eigenvalue, and similarly 0 2 is the eigenvector corresponding to the eigenvalue 0.5. In the previous case, 1 0 is the eigenvector with the eigenvalue 3, and sorry, 0 1 is the eigenvector with the eigenvalue 3, and 1 0 is the eigenvector with the eigenvalue 2. Okay. So how do you actually find out these eigenvalues and eigenvectors given a matrix? Okay, so if I just give you this matrix, how do you find them? So for that, we'll go back to the relationship that we have between the eigenvalue and the eigenvector, which is this. So for lambda to be eigenvalue and v to be the corresponding eigenvector, this has to be satisfied. This essentially implies that this should be true, where In is the n cross n identity matrix. Okay, so this is a n cross n identity matrix. Okay, let's stick to that. Now, if this has to be 0, then, and of course, please note that when we talk of eigenvectors, we are talking of non-zero vectors. Okay, so if you remember in the previous lectures, I had mentioned that if we are going to be using zero vectors, it will be specifically said that it's a zero vector. If it is said that it's a vector, then it's basically referring to a non-zero vector. Okay, so eigenvectors are essentially non-zero vectors. Now this has to be satisfied. If this relationship is satisfied, then lambda will be eigenvalue and v will be the corresponding eigenvector. Now if this particular relationship here has to be true, where v is not a zero vector, then a minus lambda I n has to be a non-invertible, or what we call as a singular matrix. Now for a non-invertible or a singular matrix, it means that the determinant of the matrix has to be 0. So this essentially means that the determinant of a minus lambda I n should be 0. You can also write this as determinant of lambda I n minus a should be 0. Doesn't matter, both are the same. Okay. So if you can find a value of this lambda, which we are referring to as eigenvalue, if you can find a value of lambda such that this relationship is true, then the lambda is said to be the eigenvalue corresponding to the matrix A. Okay, so now this determinant here, it yields a polynomial of degree n. Okay, yields a, I'll say, real polynomial of degree n. So we'll represent this real polynomial, let's say, as this symbol. So this is that triangle or the big delta, capital delta of A is the real polynomial derived from the determinant of A minus lambda I n, and this polynomial is termed as the characteristic polynomial of matrix A. Okay, so solving the relationship that determinant of A minus lambda n equal to 0 is essentially finding out the roots of the characteristic polynomial of A. So I can state that the roots of the characteristic polynomial lambda A are the eigenvalues of matrix A. And how many such eigenvalues you will get? Because this is a polynomial of degree n, you will get n number of eigenvalues. There are n eigenvalues of A. Now the question remains, are all these n eigenvalues different from each other, or are they same, or how many of them are same and how many of them are different? Are they going to be real? Are these eigenvalues going to be complex? Okay, so we'll see to that soon. For that, let us take up an example. Consider a matrix A which is possibly of this form. Let's consider this matrix. This is a real matrix. We need to find what are the eigenvalues. So here what I do is I'll take the determinant of lambda I3 minus A, which essentially is the determinant of this matrix. Okay, so I'm going to label this as the capital delta of A. The characteristic polynomial is going to be, if I solve this, I get lambda cube plus 6 lambda square plus 11 lambda plus 6 is what I get. Now the roots of this characteristic polynomial, if you see, are minus 1, minus 2 and minus 3. So these are the eigenvalue of the matrix A. So there are three roots of this characteristic polynomial, and all these three roots are real and distinct, and minus 1, minus 2, minus 3, and these three are the three eigenvalues of the matrix A. Okay, now once you have this eigenvalue, how do you find the corresponding eigenvector? So for this, we'll resort back to the fact that AV is equal to lambda. We'll first solve it for lambda equal to minus 1. Okay, assume that V has this structure. Since the matrix A is real and the eigenvalue obtained here is also real, the vector that we are going to get is also going to be a real vector, and hence ABC are going to be real. Okay, A is real, lambda is real. This implies B is going to be real, and for us uh, n is equal to 3. Okay, so I'm assuming that this is the structure. So we'll use the relationship and equate it to, for lambda equal to -1, lambda v is minus a, minus b, and minus c. So from here you'll get 3 linear equations. The first one, if you see, is saying that b is equal to minus a. The second one says that c is equal to minus b, and the third one says that minus 6a minus 11b minus 6c is going to be equal to minus c. Okay, from here, from this set of equations, you can observe that this is going to have infinite number of solutions. Okay, now, so what is the eigenvector that you should actually get? So you can observe that if b is equal to minus a and c is equal to minus b, which is in fact going to be equal to a, if you substitute this relationship in the third equation, which is this, you will end up satisfying the third equation. Okay, so here the eigenvector is going to have a structure which will be a minus a. This is what you'll have. Okay, you can conveniently choose a to be equal to 1 and say that the eigenvector is going to be, I'll label this as v for lambda equal to -1. So eigenvector corresponding to this is 1, -1, 1. This is my choice. Okay, the value of 1. You can have anything. So this indicates that there are infinite number of eigenvectors, but all those eigenvectors are a scaled up version of this 1, -1, 1. You can choose a to be equal to 2. So then your eigenvector would be 2 minus 2, 2. And the other eigenvectors are the scaled up version of this eigenvector. You scale it up by a real scalar, this you will get another eigenvector. Okay, just choose one. The remaining eigenvectors are going to be linearly dependent on this eigenvector. Okay. Now similarly, if you go for lambda equal to -2, let's say I am trying to find the eigenvalue corresponding to -2. I'll label them as D, E, and F transpose. Again, this eigenvector is going to be a 3 cross 1 real vector because A and the eigenvalue are actually real. So you have this with DEF going to be -2D, -2V, and -2F. It's lambda times V that you have. Again, from this set of equations, what you end up is E is going to be -2 times B, F is going to be -2 times E, and then you have -6D, -11E, -6F to be equal to -2 times F. In here also, if you observe, this is nothing but going to be 4 times D, And if you substitute the first two relationship, E equal to minus 2D and F equal to 4D in the third equation, you see that the third equation is already satisfied. Okay, so now what I can say about the eigenvector structure is it is going to be D minus 2D and 4D. If you want to verify, you can just put this. If you have minus 60 and minus 11, so this is minus 60 and minus 11E becomes 22 times D, and minus 6F becomes minus, I think, 24 times D. So this in total gives you minus 28 minus 8D, and on this side also you get minus 8. So LHS is equal to RHS on this substitution. Okay, so that is how you can find. Here again, what I'll do is I'll choose D to be equal to 1, thus setting my eigenvector at 1, minus 2 and 4 transpose. Okay, so this is my eigenvector corresponding to lambda equal to minus 3. Yeah, sorry, lambda equal to minus 2. Now, if I want to do the same for lambda equal to minus 3, you can, if you take the eigenvector corresponding to minus 3, let's say that it is represented by GH and I transpose belonging to R3. In that case, what you end up getting is the eigenvector is going to have the structure of G minus 3G and 9G transpose. And again, I'll choose G to be equal to 1, giving me my eigenvector. Please verify if this is correct or not. So the eigenvector that I am claiming is 1, minus 3 and 9. Okay. So for lambda equal to minus 1, lambda equal to minus 2 and lambda equal to minus 3, we get the eigenvectors. Okay. Similarly, if you take another matrix A, we'll take a 2 cross 2 matrix this time. Let's say the matrix is 1, minus 1, 1, 1. Let's say the matrix is this. So determinant of the characteristic polynomial that we'll get is essentially lambda minus 1 plus 1, 1 and lambda minus 1. That's minus 1. And this is going to give me lambda minus 1 squared plus 1. This is my characteristic polynomial. Want to expand, I think this will be lambda square minus 2 lambda plus 2. Now it is going to look like. So if I want to find the roots, I'll just equate this to 0, and when I solve this, I find that my eigenvalues are 1 plus j and 1 minus j. Okay, so here the eigenvalues are complex. Also notice that for a real matrix, when we compute eigenvalues, if a complex eigenvalues occurs, then the matrix will have another eigenvalue which is also complex and is a conjugate of it. So complex eigenvalues always occur in conjugate pairs. Please note this. For a real n cross n matrix, complex eigenvalues occur in conjugate pairs. Okay, now what we have got here is one eigenvalue is this and the other eigenvalue is this. Now, as per the definition of the eigenvalue eigenvector, we have to satisfy this particular relationship, right? Now, A is a real matrix and lambda is a complex number in our case. So, this implies that V has to be a vector in the complex domain. Okay, so it will be a vector whose tuples are possibly complex, all of them. Fine. So how do we solve for such cases? So consider the case when lambda is equal to 1 plus j. V will be of the form of, let's say, u plus jw, where u and w both are vectors in R2. This is what you will have. Fine. Now, the matrix that we considered, I guess, is 1 minus 1 1 1. Yes, 1 minus 1 1 1 multiplied with u1 plus jw1 and u2 plus jw2, where u1 u2 are basically tuples associated with u and w1 w2 are tuples associated with w. This is going to be equal to the eigenvalue 1 plus j multiplied by u1 plus jw1 and u2 plus jw2. This is what you have. Now, if we write out the equations, what we get is u2 plus jw2 minus u1 minus jw1 is going to be u1 minus w1 plus j u1 plus w1, right? So 1 into u1 and j into j w1 is minus w1. Similarly, you have u1 plus w1. Next equation that you get is u1 plus jw1 plus u2 plus sorry, I made a mistake here. So this is u1 plus jw1 minus u2 plus j minus jw2. And u1 plus jw1 plus u2 plus jw2 is equal to u2 minus w2 plus j times u2 plus w2. So if you equate the real and the imaginary parts, what we get is u1 minus u2 should be equal to u1 minus w1. Then you have w1 minus w2 should be equal to u1 plus w1. Then you have u1 plus u2 to be equal to u2 minus w2, and w1 plus w2 to be equal to u2 plus w2. So if you solve this, what do you get? So this tells me that u2 is equal to w1 then from here I get u1 to be equal to minus w2. Here I get u1 is minus w2, and here I get w1 is u2. So essentially what I have got is if u is u1 and u2, then w is, so the eigenvector u is w1 u1 u2, then w is w1 is u2, so w is u2 and minus u1. Okay, which means the vector v corresponding to lambda equal to 1 plus j is of the form u1 plus j u2 and u2 minus j u1. Okay, so for simplicity I can set my u1 to 1 and u2 to 0. So this gives me that my eigenvector is, this is my choice, u1 equal to 1 and u2 equal to 0. You can have your choice as well. I put that, what I get is 1 and minus j. This is what the vector corresponding to eigenvector corresponding to lambda equal to 1 plus j is. Now what is the eigenvector corresponding to lambda equal to 1 minus j? Okay, for that we'll revisit the relationship av equal to lambda. So we have av to be equal to lambda times v. Now A is a real matrix, so take conjugate on both sides. If you take conjugate on both sides, what you get is A B star is going to be equal to lambda star B star, right? So this essentially indicates that if lambda is complex and v is the eigenvector corresponding to lambda, and lambda star is the conjugate of lambda, then the eigenvector corresponding to lambda star is the conjugate of v, that is, it is v star. So the eigenvalue of V, so eigenvector V corresponding to the eigenvalue 1 minus j is just a conjugate of eigenvector corresponding to the eigenvalue 1 plus j. So in our case, it will be 1 and j. You have your eigenvector. Okay. I leave as a task to you to see this. Are the eigenvectors linearly independent? Okay, are the eigenvectors linearly independent? So we have taken two examples. One was for the 3 cross 3 matrix, another is for a 2 cross matrix. Check whether the eigenvectors are linearly independent or not. So we'll stop here. Thank you.